Okay, so the next thing we need to do is calculate what are known as a centered product sums. Okay, so this is just, okay, the difference between the x value from the mean, how far your x value for your data is from the average x value, square it, and then take a sum of all those squared differences. So this is like sum of residuals, but it's just difference in the x values from the mean x value. And then give a weight for each one of those. So that's SXX. And so let's calculate SXX, the centered product sum for the x values. So we're going to say this is equal to sum product. And then you have your weights, comma, SXX would be, what was it? X values minus X centered, right? So, and you have to square it. So let's do parentheses. Okay. X values minus the mean X, right? And then B14, let's just make that absolute to make sure that it's the same number that's subtracted from all of them. Close parenthesis, and then caret 2 to square it, and then close parenthesis. Okay, so C4 to C7 are the weights. A4, A7 minus B14, that's X minus X bar, X minus X mean, and then that is squared. And you should get 2000 there. And ignore the error. Let me know if you're having trouble. The next thing we need to do is SXY, okay? So the product of the difference of the distance between the X and the average X and the Y and the average Y, the product of those two, and weighted by whatever the weight is for your data points. So that's SXY. So let's go ahead and do that. So this is going to be equal to sum product. The weights would be column C, right? Comma. And what we're gonna do, open parenthesis, X values minus the average X mean, okay, sorry. And I have to press F4 to make that absolute, close parenthesis, times, open parenthesis, Y values minus the average Y value, mean Y value, make that absolute, put dollars before the B and the 15, close parenthesis, and then close parenthesis one more time. That's SX1. And ignore the error. Okay, still with me? Let me know if you need time to catch up. All right, so now let's calculate. Now we can calculate the slope. Slope is just the ratio of SXY to SXX. So let's do that. So the slope is just equal to SXY divided by SXX. 0.7089. And the y-intercept is just the average y minus the slope times the average x. Y bar minus mx bar. Y mean minus mx mean. So this is going to be equal to the average y minus m times the average x. That's your y-intercept. Okay? So that's how you calculate m and b. And we can check if that is correct using Linus, because what we just did is an unweighted regression. We assigned the same weights to all our data, right? So mm, it should give you the same answer as line S. But let's see. Let's take a look at what the instructions are here. Let's calculate chi-square first, and then we can do all the other calculations. Chi-square, that's the sum of residual squared. So this is your residual, experimental y minus mxi plus b. Okay, so experimental y minus the best fit y, you square it, and then you weight it, and then add up everything. So let's calculate chi-square. Chi-square, sum of squares of the residual. So this is going to be sum product, open parenthesis, the weights, comma. So C4, C7. What was it? What was that formula again? The y values minus the fitted calculated y values. So y values minus the calculated y values. Okay, now, before I do that, let's just calculate the y values first. You'll notice over here, this is our calculated y values. We can calculate these now. Okay, so this is going to be equal to y equals, the calculated y value would be equal to m, and then we're going to make that absolute, $18, so we can copy that down, times x, which is this one, plus b, which is this one, y equals mx plus b, and then b, our b has to be dollar, we have to make an absolute reference to that cell B19, so we can make a copy. All right, so 172.71, and look, the experimental y value is 172.86. Our calculated value for the best fit line is 172.713. If you copy that, you compare these numbers to these numbers, you can see they should be very close. 185.26, 186, 203, 201, 213.9, 215. And I've set up the graph here to automatically update based on the numbers that show up here. So you can see there's your best fit line. Okay. Now you can actually calculate this one as well. For X, the reason I put these extra rows here is so you can extrapolate your graph. So I wanted to go to zero. I want to calculate the best fit line going all the way to x equals 0. So I can copy this formula over here to over here, and you'll notice that the blue line here stretches out towards 0. Okay. So this one right here calculates the best fit line at x equals 0. So I can specify what the lowest and highest values are for my chart would be, okay? And here for x equals 100, notice your data is from 20 to 80, so it's good to stretch out your line from 0 to 100. Nice round numbers, easy to read from the graph. So this one right here, I can just copy this formula right here to here. Okay, that's going to be 229. So at 100, you can see it's around 229. This is 230 right here. Okay, and so there's 229.4. So you've got your calculated y value. So how do you determine chi-square? You can just say that's equal to 1. The sum product of the weights, comma, and then the difference between the experimental y value. So I'm going to put parentheses, y value, experimental y value minus the calculated y values. Okay. Notice there's a 1-to-1 correspondence there. Close parentheses and then square. That's the sum of residual squared. The sum of the squares of residual. All right, so that's how you calculate your chi-square. All right, let's just compare the slope and the intercept that we have here to what your Linus output gives you. Because remember, this should give you the same output as Linus because we have equal weights for all our y values. So how do you do a Linus? Remember from last semester, you need 2 columns, one for the slope, one for the intercept, and 5 rows. Okay, you can have all the statistics information that you can get from the data, from the regression, right? So highlight 2 columns by 5 rows, and the type equals Linus, open parenthesis. The known y values would be these 4 numbers, B4 through B7, comma. The known x values would be these numbers, comma. You want to calculate your b, you don't want to force it to 0, so you type true here, comma. And then the last part right here, you enter true because you want regression statistics, true, close parenthesis. And then instead of typing enter, you do Control Shift Enter. Look at the comparison right here. This is Excel doing an unweighted regression. The slope, according to Excel, is 0.7089. The slope, based on what we just manually set up, is 0.7089. Okay. The y-intercept, according to Excel, using Linus, is 158.535. Our y-intercept is 158. That's assuming all. So you can see there's good agreement between what we set up. So this is a good way for us to be confident that the calculation setup, the template we've set up for weighted regression is correct. It should agree with the unweighted regression if all your weights are 1. Okay, so let's do delta m, the uncertainty in the slope. Here's the uncertainty in the slope. Okay, you take chi-square, you divide by n minus 2. This is the degrees of freedom here. Okay, instead of n minus 1, it's n minus 2. Because you have 2 parameters, slope and slope and intercept, and then times sx. So chi-square divided by n minus 2 times sxx, and then you take the square root. Okay, so let's do that. Delta m equals square root of, what was it? Chi-square. Chi-square is this one, divided by n minus 2, so parenthesis n minus 2, okay, divided by, because you got a product in your denominator, sxx. Sxx is 2000 here, and then close parenthesis. Okay, so dividing by n minus 2, and you're also dividing by sxx. If you want, you can put b10 minus 2 and b16 in parentheses, and then you multiply them. You should get the same result. Okay, so that is your delta m. Look, compare that to the uncertainty in the slope according to Linus. Linus says the uncertainty in the slope is 0.055739. According to our setup here, our formula is 0.055739. It's the same answer. Okay, and then delta B, uncertainty in B, the formula for that is this one right here. It's delta M, uncertainty in slope, times square root of sxx over s plus chi-square. Okay, so let's go ahead and do that. It's equal to the uncertainty in the slope times the square root of something. So it's equal to delta M times the square root of, let's see what we need to take the square root of, sxx over s, square root of sxs divided by s, and to that you add the square of the mean of the x value plus mean, x mean, or is it x, plus x mean squared plus x mean squared. Let me see if I have everything right set up. Yeah. close parentheses. And here you can see your delta B, your uncertainty in your slope, and your y-intercept is 3.052955. And that's the same uncertainty that Linus gives you, 3.052955 right there. And that one. Okay, they're the same. All right. Let's compare what we have here in the Linus output with what else we have in our calculation. Look at chi-square. Where do you think chi-square is in the Linus output? Notice our chi-square is 12.42738, and it's right here at the bottom right corner. This is chi-square. That's the sum of the squares of the residual. That's where Excel puts it. Okay? So I'm going to pause again so you can get caught up.